Any question about the previous session? In the previous session, we come to this point that previously we have seen generative models in the classification method. And today we want to talk about that method and then go to some foundation material. Okay, you have previously seen the multinomial logistic regression, and as we know, it directly modeled the conditional probabilistic model over the labels given the inputs. So you have no information about the characters about the space on the inputs or manifold where the inputs lie on. These are the information. These are the definitions for different parameters here. It is not very important, but we know that given an input, you have an affine transformation and then a softmax nonlinearity which generate the parameters for a categorical distribution. Using this softmax, you can have any type of vector here. The softmax makes it a suitable vector for categorical distribution. So one example for this model is, for example, you have features, images of living room, bedroom, and dining room with these labels, and then you try to estimate the label given the input. So you vectorize the image. The image can be of a high dimensional, and then in the output of your model, you have a categorical distribution. Given the input, you have a categorical distribution. This categorical distribution define the probability for each class. For example, the class of living room have the probability of 0.1, and the bedroom 0.7, and the dining room 0.2. So you have a generative model, but the generative model is over the labels, a low dimensional space. So you can sample from this generative model. We have the procedure to sample from this model in the last part of this presentation. So if I sample from this model, because the second output, the second parameter have the highest value, you generally see 2 in the output of your sampling procedure, and sometimes maybe other than that. But you have previously know the discriminant analysis model. What is the discriminant analysis model? The discriminant analysis model models the probability over each label using class conditional probabilities. These are not named class conditional probabilities. This is the result of the Bayes rule. It is very simply derived from the Bayes rule, and these are the definitions. So I want to emphasize on this probability distribution. As you can see, if your input are images of, for example, living room, bedroom, or dining room, again, this X is a high dimensional random variable. So you have previously in the discriminant analysis model, modeled some generative model over high dimensional random variable. But remember that in the discriminant analysis, you generally assume a very simple form for this probability. What do you usually assume for this probability? Usually you use Gaussian and estimate the mean and covariance matrix for that Gaussian, and then you model this distribution. Okay, just by estimating a vector and a matrix, you estimate the distribution. It is very simple, but it is a generative model. It means that it can generate samples of your random variable X, given the class label. It means that you can generate samples. For example, in an assumed model, assume you have modeled the living room, dining room, and bedrooms. So given each of those probabilities, you can generate images of bedrooms, images of living rooms, or dining rooms. One important point is about the number of parameters. The number of parameters for the discriminant, and then for the multinomial logistic regression is this size, where C is the number of classes, B is the dimension of the input X. This is the number of parameters for your first modeling approach, which is multinomial logistic regression. But here you have this number of parameters. If you use a multivariate normal to model the class conditional densities. So the number of parameters is drastically increased. So what is the benefit of this increased number of parameters? Again, using discriminant analysis, you can estimate the label given the input. And the most important part is that if you have access to this distribution, class conditional distribution, it means that you can sample from this distribution, and as a result, you can generate images from label 2. Label 2 is bedroom. You can generate sample of bedrooms. It is not very clear now how you can do this, but at the end of this class, you can easily do these types of generation. Okay. But the most important point is that what happened for the increased number of parameters? What do you gain as a result? By the generative model, I know how the bedroom images look like. Why? Because I have a density that can generate those types of images, you know? So assume I have an input image, where some input pixels are missed. I have a cropped, for example, image of a bedroom. If you input this type of image to a multinomial logistic regression, because the multinomial logistic regression can only model the relation between the input and output. It cannot understand which type of the input is legitimate. This type of input is not legitimate for a logistic regression, because the logistic regression is trained on the fully visible images, not the image which is cropped. Okay? So this is not from the distribution that this model has learned. So as a result, in the output, although you expect the second probability to be high, but the first one is higher. So it's assumed that it is I think, dining room. Yeah, it is a living room, while it is a bedroom. So why this happened? This is not a bad model, but in the input, you give it something that it has not ability to model. And in the learning, it cannot see something like that. But what happens when you use a generative model? When you use a generative model, you can easily do what? You can easily partition your images to two parts. One part is the visible part, one part is the masked part. This is what we can do at the end of this class, but I want to give you intuition how it works. I can partition the image into two parts. The first part is the visible, the second is the masked part, and I can generate this distribution. What is the difference between this distribution and this one? I just conditioning on what I am really have from the input. The input is not fully visible. I just have access to the a part of the input. So I just condition on those parts and then generate the label. So I do not enter these masked pixels in my decision. And it is much more robust than the above.
How do you do that?
This part. It is the result of marginalizing out the masked part, but at the end of this course, you easily can do these types of tasks. But one simple idea is that, for example, just to have an intuition, we have access to this, yeah, in the logistic. In the discriminant analysis, you can generate the distribution over X. How? By marginalizing out over Y. I think those who sit down there cannot see what I'm writing. I have access to this distribution. I can marginalize out Y. How? And using conditional I can write it as this distribution. So in the discriminant analysis, I have access to this and this distribution simultaneously. So I can generate the distribution over X. One idea is that you can fill the missing part using this distribution. How? You have a visible part and you have a masked part. They are the same because visible part and masked part, if you concatenate them together, you have the full data. So if I maximize this distribution over the masked part, assume that this distribution gives me the ability to do this optimization. If I mask the distribution over the if I mask the distribution over the total image over with the random variable of the mask part, I mean that which image in the masking part can better lie on my model, which of masking is better to fill the image. The generative model gives you the ability to find that masking. So you have a complete image, then you can fill that image and then again estimate the label. This is one approach. The other approach is this. But this is also the one approach you can use the information in your generative model to fill the missed parts. Okay. This is the end of. Yeah.
Yeah, so basically that's two max operations, right? It's one max over y and one max over x.
Yes, yes. It means that first you fill your image, you have a legitimate image now, then you give it to your discriminant analysis, your original discriminant analysis without any change.
Yes, so is that relationship embedded by default, or do you have to first of all derive the probabilistic expression where you have marginalized?
By marginalizing out the masked part, it means that you are considering all of the different types of masking. You know that. Assume that I consider all possible masked part. How someone can fill the masked part. I consider all of them and then do my maximization over the best one there. This is what I'm doing here.
So you don't have to retrain the model.
No. But you have an extra optimization. It is not as simple as, for example, one feed forward of the network. No. You have another optimization because you want to fill the masked parts. This is another optimization. But the last optimization over the labels is the discrete because the labels are 1, 2, 3, 4, or L. This is very simple. You are easily can compute. But this optimization is not simple yet. Yeah.
Just a question. So, when you say that you're considering any type of XM over there that on the board that maximizes the probability of X, so the model can fit any pixel on the mask bar to make it a complete image, right?
Yes.
So I think in that case it makes it non-robust image because, for example, a model can place a dining table on the right and make it very similar to the dining room without any correlation between the pixel on the right and the pixel on the left.
Yes. The model know that the first part is this. And it fills the rest of the image based on this part. Completely correlated to this part, it fills the image. It is not an independent from this part. Because your model see both of parts together. It does not mean that it puts the visible part aside and have an half image and wants to fill it. No. It fills based on your visible parts. Yeah. They are completely correlated. Any other question? Okay. So we are now at the start of our big picture. What we want to do here? What do we have? We have data distribution, you will see several times this notation. We have a true data distribution that can generate images, that can generate sounds of, for example, some keywords, that can generate some text, anything else. Any modality you can consider. You have a true data distribution, and you have a family of all possible distribution. We can assume that the all possible distribution can be contained in this box. What do we want? We want to do, the first task is to select a family. We want to select a family inside this complete box. These are all possible distributions we can consider. And we want to select a subset of that, which is parameterized by theta. It is always this one. We always want to parameterize the distribution using theta, so you always see this notation too. So when I have this distribution, what I want to do is, when you change theta, you move in this subset, okay? I want to move this in this subset such that a defined the distance metric like L is minimized. So the preliminarity for this process is that I can define a distance metric between two distributions. It is completely different from our previous, maybe our previous distributions, the distance we have learned. We want to define a distance metric between two distributions, and pay attention that I do not have access to the true database distribution. I have just samples from the true data distributions, which are these images or text or voices or anything else. So the first step is defining the family. The second step is to design the distance metric, and the third step is to minimize this distance, the metric. So at the end of the day, I am in a point which is the best point in my family from the distance metric to the true data distribution. So in all of our models, we have these three steps. First, we define each of them separately. First, define a family. Second, define a distance metric. And finally, define the optimization procedure, which results in a theta star. Theta star is the best set of parameters based on your family. Okay?
Just is it just visualization? How do you set the boundary, the red cloud tube?
Yeah, it is just a visualization, and but it is true that we do not work on the total family.
Right. So how is that defined? Like I know it's visualization, but is it defined by the model capacity? Is that
yes, exactly.
Yeah. It is the most important part to define this family is the type of input you are working on. For example, if you are working on text is something temporal. It has a sequence. Mm-hmm. Or if you are working on voice, it has a sequence. If you are working on an image, it is a batch signal. Mm-hmm. All the pixels are together in your input. It is based on the input, what type of the input, and different models can provide the best performance in different type of modalities. For example, autoregressive models are very well tuned to temporal to sequence data. Yeah. This is exactly based on the type of the input can be defined. So we have two selections here. One selection is why we do not consider all possible data distribution. Do you have any idea why don't we consider this state? We do not limit ourselves in the selecting the family. We search over all possible ones.
Too much. Computationally expensive to search.
Yeah, exactly. If it is computationally expensive, you see this even for the MNIST data set, which is a really simple and which cannot be a real world data set. This approach cannot work. So we we are forced to select a family and then do the optimization over that set of family. So let's start with a very simple generative model. A generative model that wants to model the output of tossing a coin. If you toss a coin, you have two states, 0 or 1. You want to put the coin aside and start your generative model to generate the results. This is again a generative model, but a generative model over a binary random variable, which is very simple. So, assume we have a Bernoulli random variable, and this Bernoulli random variable can be denoted by this notation. The beta parameter shows the parameter of the Bernoulli distribution, Bernoulli random variable to be 1, and the 1 minus beta is the probability of being 0. In this case, your family is very simple, your complete family. How many parameters the complete family, the blue box have? For this example, exactly 1. Because by changing the beta, you can sweep all the space. You have just 1 parameters to totally model the family. But sometimes, for example, you can limit that parameter. For example, between 0.2 and 0.3. This is a family, a subset of that whole space. So we are becoming familiar for the family selection, how we select the family. For example, in maximum posteriori estimation, sometimes you put some information about the theta. For example, you assume that theta is in this box. So in this case, you are limiting the family from the total space. So now assume that with any method, yeah.
Just a quick question. So by family, you mean the number of parameters, basically, as you mentioned?
Yes. Yeah, exactly. Generally, we think that by selecting the family, the number of parameters is dropped. But here, because we have just 1 family for the total family, it is not the drop, but it is just limited. Yeah. But in the case that we are working with more complex families, you see that it really drastically drop the number of parameters. Yeah.
Here, what does the family represent? I don't think I've quite got that.
The family is a Bernoulli random variable. A Bernoulli random variable is a random variable which is in the sets 0 and 1, and it can be modeled by using just 1 parameter. These parameters show the probability of 1, and 1 minus this shows the probability of 0. This is the total family. If you toss a coin, you are in this space. Because the coin have a parameter for being 1 and 1 minus beta for being 0. So if you toss a coin, it means that you are using this family. Any binary random variable, not the...
So here the family would be defined by the value of beta?
Exactly. The total family is defined by the parameter beta. Yeah. And when I limit it, it means that, for example, this is the total family 0 or 1. This is the value of beta. And when I limit it, for example, I am in this space. If this is my subspace, this is the whole space. So assume that by any method, I optimize the theta for this family. It means that I find the theta star for a Bernoulli random variable. So we have 3 tasks, but 2 of them is generation and density estimation. How can I generate data after I understand that the theta for this coin is theta star, the best theta is theta star? You can put the coin aside and start generating using your generative model, okay? I can easily sample from a uniform distribution between 0 and 1, and this is the value of theta star that I find using any optimization method. I do not want to talk about that method because you will learn about it during this class. So after having access to this theta, I look at the uniform data which is generated. If this data is between 0 and theta star, I output 1. And if it is greater than theta star and below 1, and I output 0. So assume that the theta star is equal to 1. What does it mean? You always generate 1. And it is similar to your coin, because the coin is always generating, for example, head. And the other task is density estimation. The density estimation is very simple, because theta star itself is the probability of being 1, and 1 minus theta star is the probability of being 0. So I can do both of the tasks, both generation and density estimation, with very simple example. So it can also be extended to the example of rolling a die. I do not want to explain it more, because the idea is exactly similar. I assume that in the rolling a die, here you have 5 parameters. Why? Because you have 6 parameters for each of the results, but the summation is to 1, so you have 5 parameters. Here, the number of parameters is written. You can, for example, assume that the probability for 1, 2, and 3 is equal, and the probability for 4, 5, and 6 is equal, so you have 1 parameters. And this is a subset. The whole set have 5 parameters. Here, the number is also dropped. Your family have 2 number of parameters, so you are selecting a subset of this whole family, and you work on the subset. The number of parameters is reduced. Especially when you have limited number of training samples, you can see that this model can really work better. So
yeah, how do you decide these constraints? Like, you have to get some domain information.
Yeah, exactly, and domain and the input. Exactly, the input is much more important. How you limit the model. For example, in the autoregressive models, you see that your limitation is exactly similar to the nature of the signal. It uses the nature of signal, which is a temporal nature, to model your family, which is a subset of the total family. Yeah. Here is just an example. It is not, no intuition is behind the modeling here, just to see that how you can model, you can limit the number of parameters by limiting the subset you can select. So assume that by any method I can design this generative model and have the theta star vector, because theta star here is a vector, these thetas. How can I generate? Again, I can sample from a uniform. If this uniform is between 0 and theta star, the first element of theta star, you output 1. If it is between these 2 numbers, the output is 2 until the end, which is the 6. You can see that you use the cumulative probability to generate the samples. If each of these theta star is a large value, the corresponding boundary for that value is increased, so that the probability of outputting 6 is increased. This is the way you generate samples, and this is again the density estimation. For each of them, for xi, the density estimation is theta star I. So I have a generative model. So can we work with this idea for real-world examples? No. Can we extend this idea to real-world example? No. Why? Because assume that I have one RGB pixel, just one RGB pixel, not an image, just one RGB pixel. Then each of the R, G, and B can be in this set. So the number of categories you have is 55 to the power of 3. What does it mean? It means that if you want to really consider all possible states, it becomes intractable. for one pixel, it is to some extent interactable, but for a total image, which is, for example, 1000 by 1000, it becomes really interactable. And the number of parameters to model this category is this value. As you know, the number of parameters for one pixel for the total space is 255 to the power of 3, the number minus 1. Why minus 1? Because the summation should be equal to 1. So even for one pixel, you must limit the family. So selecting the family is one of the most important tasks you have here. Okay? Samples are not Bernoulli or are not simple categorical. They are categorical, for example, like this. This is again a categorical, but the number of categories is very high. So selecting is very important. Another example, assume that we are in the real world binary image distribution and X have this distribution. We will become familiar with the notation in the next presentation. This is just the introduction. So assume I have an image with n pixels. N is the number of pixels. So I have n random variables. Each of them is binary. Okay? I have n pixels. Assume that I have vectorized the image, and I have n pixels, 1, 2 to the n. Each of them is binary, 0 or 1, 0 or 1. So, what is the number of different images I can have? It means the number of categories. I want to model it using a categorical distribution, yeah? Because it's 0 and 1, so I have categorical distribution. What is the number of categories? The number of categories is 2 to the power of n, because each of them can have two states, 0 or 1, and the multiplication of n2 is 2 to the power of n. So to model an image with n pixels, a binary image, very simple, you need 2 to the power of n minus 1 parameters. So again, interactive. So you must select a subset. You cannot work with the whole set. Okay? So assume that I have access. I work on the total family. Then and find theta star. This is a wish. This is not. This cannot be worked in practice. Then, if I sample from that distribution, assume that these are the mth digits. Then, if you sample from that distribution, you see these types of images in the generated samples. We will see how to generate samples using, for example, a distribution. But here we ideally assume that we can access to the complete set of distributions and can find the theta star in that space. It means that this state, you have access to the whole family, you go to the best point. Okay, so how can I reduce the number of parameters for this example? Binary image. I want to have some ideas to reduce the number of parameters for this example. So, one idea is to assume that each pixel is independent of all other pixels. What happens if I assume this? The number of parameters, how does the number of parameters change? You just need one parameters to model this one. Assume, I call it beta 1. One parameters for this one, and one parameters for this one. So the number of parameters reduces to n. In the previous state, you assume each of the total of these images as one category. Now you separately, why? Because you were considering the correlation between all of them, all the possible categories. But now you just consider one pixel and say that it is not relevant to other information in that image. So I can model it with one parameter. So in this state, I have n parameters. The number of parameters changes from 2 to the power of n minus 1 to n. So the subset is here. You select a very small subset of the whole set, but what happened is that if you even train the resulting model, you will see how to train the model. You will have the model that generates images like this, which are all garbage. Why? Because in your modeling, you do not consider the correlation between pixels. You are modeling each pixel separately. What does it mean? It means that, for example, assume you have in the image, in the MNIST, you have 6,000 image, okay? What do? You extract the first pixel of all images, put all the pixels aside, so you have 6,000 binary random variables, and then model this one, just this one, the first pixel, and then estimate beta 1. Put it aside, then the second pixel, then the third, then until the last pixel. Just separately you model them. So you do not understand the correlation because you do not even see two pixels from the same image simultaneously. You just see the first pixel, the second pixel, the third pixel. So you put aside the correlation, and this is the result. These are the generated images. Why? Because you make a very small family, and even in that family, if you find the best parameters, those parameters do not work. The result is this. Okay, so the modeling is very, very, very important. How you model your subsets. You cannot easily assume that they are independent, so I can't model the result. I know that the number of parameters is drastically reduced, but the performance is also reduced. Okay? So, what can I do? What can I do such that I, at the same time, control the number of parameters and at the same time increase the size of that subset intelligently, not in any way?
Create a mask.
What?
Create a mask.
Create a mask. How? Well, you mean the mask parts are not correlated, for example?
Kind of.
Yeah, that's an idea. In other words, we can write using, we have a rule in probability which is named chain rule. You may be familiar with the chain rule. Chain rule says that if you have a random variable, the distribution over the random variable can be rewritten as this term here. It means that the distribution over the whole x can be written as the distribution over just the one pixel, the distribution over the second pixel given the one pixel until the end. Okay? In the first example where we model the whole family, we exactly model this distribution. For the second one, that we assume the independent case, we assume that P of x2 given x1 is P of x2 because they were independent. And until the end, P of xn given the rest is P of xn. So these are two different marginals. So stay in between. Not this place, not this place, in between. What does that mean? Assume I said that each pixel is just correlated with the previous one. Not the whole previous, just the previous one. This is another family. The first family was that each pixel is correlated with the whole previous. The second is correlated with none of them. The third is correlated with just the previous one. what happens in this case, I can write the whole distribution as this one. X1 has no previous, so it is alone. X2 given X1. X3 given two previous, but if you have access to X2, X3 is independent of X1, so you can omit it here until the end. Given xn minus 1, xn is independent of the previous pixels. Something like you said. So, I think I write it here. So, if I consider the whole chain rule is equality here, so nothing changed. Again, the number of parameters is 2 to the power of n minus 1. But here I write that chain rule imposes no restriction. It is just a rewriting of the original distribution, so the number of parameters is not changed here as we expect, but assume that the case I'm talking about here. Assume that I can write the chain rule and then assume that given the previous one, the pixel is independent of the past except the previous. What happened here? The P of x1 have 1 parameters because it is a Bernoulli 0 or 1. P of x2 given x1 has 2 parameters. Why? Because it is this distribution. P of x2 given x1 equal 0. This have 1 parameters. P of x2 given x1 equal 1. This is have another parameter. So totally it have 2 parameters. And the number of parameters is drastically reduced in comparison to the original one. The number of parameters is 2n minus 1. So what happened here, if you assume the independent case, you have this set of family which is really small, and at the result you see that the generated samples are not are garbage, are not understandable. But if you increase the number of parameters in an intelligent way, such as this one, because for example in an image, the previous pixels or the pixels on the neighborhood can have some information about your pixel. So this idea is really working for the images. As a result, you increase your family. Why? Because your number of parameters is now changed to 2 times n minus 1, and it is intelligent for images. And then you can see that the generated samples using this family are similar to some extent to the real samples. This is called the first order Markov chain model. Just to know the name, it is not important in the course. So altogether, for the introduction, the first thing we should work on is to select a suitable subset of probability distribution, which we name calligraphic P subscript theta. So this family should not be too large because we have problem in learning or training. It should not be too small because the resulting model cannot model the real world data. And also it should be aware of the type of the signal you are working on. For example, if you are working on image, text, anything, in the selecting the family, you should be aware of that input type. The next one is to introduce a suitable distance metric between two distributions, which is our work in the rest of the semester. And the last one is to optimize that metric such that the parameter theta is the best one, which in that subset model the true data distribution. And finally, how to evaluate your model. You train a model, how you evaluate it. For example, in the supervised learning, you can easily work on the classification error over the validation set. What can we do here? Because we do not have any validations, we do not have any label. We can have validation set. So these are the differences. So any question about the introduction part?
Professor.
Yeah.
You showed basically what happens by kind of keeping a correlation of one previous pixel, but in theory, right, like if we want to improve performance and we have the capacity to spare, we can do 2 or 3 or 4, right?
Exactly.
Okay.
Exactly, yes. If you have the resources, you can increase the Markov chain, yeah. Okay, let's talk about some foundation. The foundation is really easy, but I just want to make sure that we are on the same page, especially from the point of notation. Because we see different notations. If you have seen different notations for priority and distributions, but I want to share the notation for the distribution here so that we can work in the rest of the semester. About the abbreviation list, I have added the abbreviation list to the previous slide, but I do not update the file in the canvas. I will update that. And you can see a table at the end of the presentation where the abbreviations are present there. Okay, during this course, I have a color code. These colors are not used in all the courses. Maybe it's based on some courses, but I use these color coding blocks. The blue blocks are, this color is definition block, this color is result block, this is the note block, this is the example block, and this is the remember block. Pay attention to the colors that they may have. Some of them may not present in the total of this course, but usually some of them I will use during the course. The most important part, the notation. Pay attention to this slide, it's very important. For a scalar, I use lowercase or an uppercase. You should understand based on the context whether it is a random or not random. If it is a random, I generally for a non-random, I generally use this one. If I have used a big X, uppercase X, it means that in a random context, it means that it's the random variable itself. It is not the value assigned to the random variable. It is the random variable. And as you know, random variable is a mapping. It is a function, nothing else. About the vectors, I use the bold lowercase representation for the vectors, and this is the random variable for the vectors random variables. And my matrix also, I use uppercase bold notation for the matrix which are non-random, and this is the notation for random matrices. We do not have much random matrices in this course. Usually we have random vectors. Okay. The ith element of a vector is written by this notation or this notation, and the ith element of a random, the ith element of a non-random vector is written by these two notations, and the random vector is written by these two. You know that if one element of a random vector is a random variable, this is aligned with the definition of the random scalar for us. Okay, for the matrix, we have this notation. For a row or a column of the matrix, we have these two notations. And if the parameter or the vector I'm using have a subscript from before, for example, if it is xk, I use the subscript for the index at the end, not at the start. This is the note I have here. This is an example, yes. Okay. About the operators, all the operators are known to you, I think, but just one operator which is different is element-wise product that I show by this sign. And as you know, it is an element-wise product. It is It's very simple. Vectorization operator is an operator that converts a matrix into a vector. The trace of a matrix, the summation of the diagonal elements, the norm, the LP norm for a vector x is defined, and three well-known norms are L1, L2, and L infinity. We generally use L2. The others are just for your information, maybe. Maybe L1 is also used. The transpose is very simple. If you have any questions, stop me, please. The diag operator, if it is operated on a matrix, on a vector, it generates a matrix where the elements of the vector are on the main diagonal and the other elements are 0. If it is operated on a matrix, it means that you extract the diagonal element of that matrix and generate a vector. The gradient vector is the vector of a function if you have a function from a vector space to a scalar space, then you can define the gradient vector for that function, which is defined as this vector. And also the Jacobian matrix for a function which is defined from a vector space to a vector space is defined as this element, where the first row is the gradient vector of the first output with respect to the input, which is not very important. I usually use LHS and RHS, as you know, left-hand side, right-hand side. This is just a notation, okay? Then I want to talk a bit about probability and statistics, and more about the probability, not statistics. Just to have a review, they are very simple, just to have a review of what we have learned before. A probabilistic experiment is defined as an experiment where the output of your experiment is not certain. For example, rolling a die, but the space that the output comes from is certain. One of these elements must happen in the output of your probabilistic experiment. If you define a numeric vector and design a mapping from the sample space to that numeric values, the resulting mapping is a random variable. So random variable is a function, is a mapping from the sample space into the numeric space like this. You can assign, for example, the output 1 and 2 to the numeric value of 1, but you cannot assign one of the element in the sample space to two different numeric values. It is exactly a function here. Okay. The next definition is the event. The event, for example, assume that I have this sample space, this mapping of random variable, and this is numeric values. The event is defined using this notation, or equivalently are the element of the sample space whose output in the random variable is the numeric value you assigned here. This is an event. For example, this event is equivalent to this set. The PMF is also another mapping which assigns a probability to each event, to each isolated event. I mean, one of the elements in the sample space, which is defined as the probability of this set. So the PMF has two properties. The first one is that the PMF should be non-negative. It is logical because the probability of event cannot be negative, and also the summation overall possible numeric values should sum to 1 because you are certain that one of the elements in your sample space will happen and they are assigned to the numeric values. Okay. One well-known probability mass function is the Bernoulli Bernoulli distribution is a discrete random variable, and the PMF for that random variable is defined as this function. Pay attention to this notation. We will have this notation until the end of this course. If I have a random variable, I show the random variable, for example, Bernoulli random variable with each of these two notations. I use both of them during the course. Here I said that x is a random variable coming from Bernoulli with parameter theta, but it is more common in this course that to write a parametric distribution with the parameter theta over the random variable x, which is a Bernoulli of random variable x or with the parameter theta. It means that the distribution here means that it is parameterized by theta. So this the distribution have very simple definition. The probability of being 1 is the theta, and the parameter of being 0 is 1 minus theta. Theta must satisfy these inequalities. The other one is categorical distribution. You are also familiar with this random variable, but here the parameter is a vector, and the vector, each element should be between 0 and 1, and the summation should be 1. So the context of random variable can be easily extended to random vectors. Assume that instead of one die, I have two dice, and I roll them together, but they are different. The color is different. So your sample space here is two-dimensional, so it is a random vector. It is two-dimensional. You can define the sample space. Each of these two is one element of the sample space. It means that at the output you have two results for each of the die. Here the numeric values is also two-dimensional, so you have a vector. Pay attention to the notation. Here it is bold, and here the notation for the random vector is also changed. The random vector here is an assignment from the sample space to the numeric values. This is here, and this element in the sample space is here, and all others can be assigned accordingly. This is the random vector. The PMF for a random vector is again similar to the PMF for the random variable. Assume that I want to evaluate the probability of random variable x equal to numeric value x. It is the probability that simultaneously x1 is equal to numeric value x1 and x2 is not equal to numeric value x2, and it is positive and it is non-negative, the probability mass function, and also the summation over all possible sample space elements is equal to 1, as we know from the probabilistic experiment. Another point is the marginalization. It means that if you want to have the probability mass function over one of the elements, you should marginalize out the other element. It means that you should evaluate the summation over all possible numeric values for the other random variable, and you can have the random variable, the PMF for one random variable. Okay. The next one is the conditional distribution. Assume that my probabilistic experiment is this experiment. At first I toss a coin. That coin, this event is 1, this event is 0, and the probability are written here. And as the result of the coin tossing, I roll a die. If I have head, I roll this die. If I have tail, I roll this die. But the most important point is that these are biased dice. It means that the probability for the one is different from the others, and the others are equal. In here is the probability for 6 is different from the others. This is my experiment, the probabilistic experiment. The random vector again map you from your sample space into a numeric space. The numeric space here for x1, I have two states, 0 or 1, because it is a binary, it is a tossing a coin. For this x2, I have 6 different states because it is rolling a die. It's based on the result of the coin. So based on the independence of these two acts, these two random variables, I can easily calculate the probability of each of these points. You know, I can easily evaluate the probability, and if you sum these values, you can see that they are equal to 1, and as you can see, each of them is between 0 and 1. This is the PMF for the vector x. So, assuming unconditional events. Unconditional events is something that we defined before. Assume that I want to calculate the probability of tail, I think, because 0 is tail. Assume I want to calculate the probability of tail. It means that I should sum the point here, the probability of points in which the result of the coin is tail, and it is these states. So if I sum them, I have 0.5. If I do not have any information, the marginalized probability over the coin is fair, as you see in the experiment itself. But one important point is that assume, they should come one by one, but we are all together. Assume that you have information that the result of the die is 6. You watch that the result of the die is 6. What happened to your belief about the coin? The conditional events are a principal way to update your belief about a random variable. Before this happening, you believe that the probability of the tail is 0.5. Now, I told you that the event for the x2 is equal to 6. You should be able to update your belief about the coin. What happened to the coin? You do not have information about the coin, but you should update yourself. So, if I said that x2 is equal to 6, it means that one of these two have happened. So, I can easily put the other elements probability to 0. But what happened to these two? What is a generic way to update these two? Before your experiment, they have a ratio. Okay? For example, this event is 5 times this event, the probability. They have a ratio. There is no evidence that the ratio changed. So the ratio should be again similar after you update your belief. So I easily update them by dividing them to their summation. I have a new word. This is my new word. This is the word of conditional event. P of x1 and x2, given x2 is equal to 6. We know that x2 is equal to 6, but I put it here because in general, we have this notation. So I have a new word where the updated probability are as written in this image. So what happened here? What is the probability of tail, given that I see that the result of the die is 6? I can easily sum this column. Yeah? If I sum it, I get to 0.83. So the probability for the tail is increased to a large extent. What happened here? What do you think? Based on this experiment, how do you justify the update in the probability of tail based on your probabilistic experiment? Why does the probability of tail increase from 0.5 to 0.83?
Because the probability. It is more likely that the first die was used because it was 0.5 for 6.
What?
It is more likely that the first die was used because the probability for getting 6 is 0.5.
Exactly. Because of this element. If we do not have any information about the coin, but we know that if the coin is the result of the coin is tail, with a high probability we will observe 6 in the output of the die. And now we see that the output of the die is really 6. So our belief about the probability of the tail should increase. Because you watch 6, 6 is not biased between these two die. The die at the result of the tail have a higher probability for 6. And this is and the conditional densities are a principled way. The conditional PMF are a principled way to update your belief when some information is given to you. We will use this idea during this course, and it is very important for us. So, just another important random variable, which is continuous random variable. Assume that before I have a die rolling experiment, and I know that they are discrete random variable, and each of these points have isolated probability. So what happens if someone tells you that I want to know the probability that the random variable is between A and B? You can easily sum the probability, these elements inside your box to calculate the probability of this event, where you know that each of them should be positive and the summation should be positive. Assume that we have another experiment in which all real values are probable. They can happen in practice. It means that you do not have isolated results. You have continuous results. What happened here? In this case, we are working with probability density functions. It means that, assume that we have an experiment such that we want to know, in a 6 hours experiment, how long can you jog or can you walk, for example? The result should be made between 0 and 6, but the result can be any number between 0 and 6. Assume that you have infinite accuracy. So in this case, what happened? What is the probability of, for example, you can jog between A and B hours? In this case, the result is defined as a probability density function. And the probability density function is a function that can provide the probability for such events for you. For example, for this event, you can calculate the probability of the event using this integral. Again, you have these two conditions. First is that the probability for each isolated point should be positive. We do not have the limitation of less than 1. And another one is that the summation, the integral, the area under the curve, under this blue curve, should be equal to 1. Because you know that if I put A to 0 and put B to 6, the area should be 1 because this is a 6-hour experiment. This is the definition of random, this is the definition of probability density function, which is suitable for continuous random variables. Some well-known continuous random variables are Gaussian distribution, as you know before. I write it with either of these two notations. X is calligraphic n. This is the first parameter, which is the mean. This is the second parameter, which is the standard, which is the variance. And this is the second notation. We usually use the second notation during this course. And what is the relation for the PDF? Here we have two equality signs. The relation for the PDF is this one. As you can see, this notation, this PDF have some interesting properties. Based on the mean value, you can define the place where have the maximum probability value, the probability density function, I mean, because they are not the probability. This is the the result of different curves for different value of mean, and this is the result of the different curves for different value of variance. As you can see, the extent of the curve will change by changing the variance. Okay, any question? Great. This is the last slide. About our notation for the probability density or probability mass function. For probability density and mass function for both of them, we use, if it is a random value, we use this one. If it is a random vector, we use this one. For the numeric probability, we use this one for scalar values. We use this one for vector values. For conditional PMF or conditional PDF, usually for the condition, we do not have a random variable, we have given variables. For example, if this is a given scalar, this is a given vector, and it means that I am looking to the distribution here. You see that this is the column of distribution. This is the distribution. But if I want to work on numeric values, I use this notation. It means that I change from this uppercase to a lowercase. I change from this type of bold notation to this one. Two important probability density or probability mass functions are the model and the data. You will see them for several times during this course. If I'm working on the model density, it means that one of the elements from that subset, that red subset that we talked about. I use this notation, P of theta with the input of x. This is the distribution. This is the numeric value in a point. If I am talking about the data distribution or the true distribution or the distribution that the data set is coming from, anything you think you are comfortable with, I use this notation, P of data with input x, or P of data with input x given y for the distributions, and these are for numeric values. I hope I have these notation during the course, but sometimes maybe I have some mistakes. You can tell me to update the presentation, but I do my best to use this notation during the course. Okay, we are at the start of expectation, and in the next session we will finish our foundation. Any question if you have, you can stay here and we can talk. Thank you very much.